live. Hello. Today we're going to talk about communication ways in microservice world. And I chose this topic just because I made some mistakes when I first started working with microservices, and I kind of want to preach some things that you do not make the same mistakes as I did. My name is Irina. I'm from Romania. I work at Endava, and I'm also a Microsoft MVP. Today's agenda will be comprised of these things. We cannot talk about microservices and the way of communicating between microservices without first talking about monoliths. It's just fair for them. Even if we moved on, the time has passed, and now we're doing nice architectures, and we kind of forgot about monoliths, but we need to remind us of them. I'm going to talk about HTTP protocol and why it's not good to use it. RPC, two different types of RPC, and then we're going to switch to messaging and see what are the basic topics in messaging as a whole concept. First of all, whoever worked with monoliths? Okay. Who loved them? Admit it, come on. Okay. I actually love to work with monoliths just because it was very easy for me as a developer, because everything was self-contained. We had a single code base. If ever I don't know, you needed the dependency was there. So you just instantiated the class, or you went to dependency injection mechanism, and you had the things in there. Unlike microservices, where you need to open several solutions and you do not know how to get to things in there. It was a single deployable unit, and the life of the developers was very easy. Just because I remember sometimes when I had a huge solution and I pressed build, and I could go out and get a coffee because the build time was humongous. So it was nice, more free time for us. Single technology stack. We're the .NET developers mostly, so we love .NET, and we couldn't find this as an impediment. But some businesses kind of need different technology stacks in their applications. All or nothing deploys. With monoliths, you knew one thing. Either it worked, the deploy, or it didn't work. 50-50% chances. And monoliths had zero or almost zero continuous delivery possibilities, just due to the fact that we're very large. Hard to test. Every time a deploy was made, an army of testers should have went there and just smoke test, regression test, and everything that was possible as a test. And it needed to be made just for us to be ensured that, well, things work after our changes. How do we scale the monolith at that time? So we had a machine, a normal, regular machine. And then the first option that we had was to give a bigger machine, right? Bigger machine meant not only storage, meant RAM and CPU power. So if you had a machine and you doubled it in size, not necessarily meant that you will pay double. The proportion of computing power and RAM and everything else is not necessarily directly proportional with the size of the machine. So that meant money, more money for our business or for our client to spend on this. So then we decided, okay, I want to do microservices, I want to do modern technologies and architectures, and we decided to split the monolith piece by piece. And then we realized that a microservice is that thing that is not a monolith, but always tends to become one, because we are not always taking care of the boundaries of our services. And the go-to things is to shove everything in the service. So micro is not necessarily a term that is real in our developer life. Micro is more like a service, a smaller service than a monolith. So this is what I used to do, and this is what happened to me. I had a service that had the tendency to grow back to a monolith size. So a microservice should have its own database and should be easy to deploy and standalone. But more often than that, ease of maintenance, um, easy to maintain. Well, that's an understatement because, well, it's not kind of easy to maintain microservices because a microservice or a suite of microservices introduces complexity. We want it or not, it's a reality. So, what do we obtain? Standalone units, but cascading effects on failure. If the service A depends on the service B, and the service B doesn't respond, service A will fail. So we'll have cascading effects. And we need to monitor them, and not always we have a DevOps around us to monitor them, to take care of these services. And then we realize that these independent units are like this and like this, and that they need data from each other and not so independent anymore or standalone. And our architecture becomes something like this. We want it or not, that's the tendency. Or something like this. But we stick to it just because, you know, Amazon kind of calls 150 APIs to build a single page. It's a small research that I did. So I got to that number. I don't know how true it is, but they surely do a lot of microservices. They have always chaos engineering and stuff and testing things directly in production. And also that Netflix has 5 billion API calls a day, and 97.7 of them are internal. We do not see them. So we think, okay, they do that, we can do that also. But the first thing that comes into our minds when switching to microservices is to create HTTP clients. Service A, Service B, HTTP clients, right? Easy to do in .NET. They are performant. We can configure them as we want. We can also introduce some logging and tracing in there. And our HTTP calls, like in client-server architecture, you you issue a request, the request is processed, and you are happy because the answer comes back. But what happens if it doesn't come back? I mean, the second API or the handler in our case maybe is down, or maybe there is a network issue and you do not get the response back. What happens then? The fact is that you do not actually know that you received the request. I mean, someone issues a request, the other side doesn't receive the request. How do you know if something was issued or not, if it doesn't reach the other end? So here we're going to see a video because I think it's easier to... The code is not important. The deal is that, you know, you issue a request and you get a response back. But let's see what happens if the response doesn't come back. Come on. No, it doesn't want to. Either way, so if a service A issues the request and to the other service and the service is down, what happens? Come on. Timeout. Okay. What other thing? Do you know what the initial request was? You wait for a response. But what was the request? You have absolutely no way of knowing that, right? Indeed, you get a timeout. But the actual content of the request, what was in it? You have no way of tracing that. Okay. So some people in the internet world and our IT and .NET world say that it's perfectly fine to use HTTP calls and the synchronous HTTP calls. So timeouts, as you said. How about availability? How do you ensure that the services are up whenever you need them? Because actually you have a location and temporal coupling. You need both systems to be up at the same time to be able to communicate. And also, you can lose the requests and not even know what the content was. How about retries? Okay, you get a timeout, but for how long do you retry? And then you said, okay, it's okay, HTTP, sync, okay. Let's switch to async because it's faster. We can distribute load. But is it? You distribute load by using async calls? Apparently, because it seems that you can process the request faster, but you actually have the same problems. It's still HTTP behind the scenes. It doesn't matter what paradigms we are using on the server side. So in here, hoping this works, what it happens is in a 20 seconds time span, I'm pushing an I as a request and incrementing that I. So we're going to see that in a 20 seconds time span, we're going to push around 3,000 and something requests. What happened to them? What if I've told you that the other side is not up, but the requests are issued? So I have pretty much 20 seconds time span wasted of our lives, and we don't know what's behind the scenes, right? So hell of a reliability, right? So talking about HTTP in general, it's synchronous by nature. So more than that, it actually opens a new TCP request for each request. No matter if you have an awesome HTTP client that you implemented yourself and you distributed it by nugget packages and so on, it's still going to make a new TCP connection. And also, HTTP has no retry out of the box. You need to code those yourself. And also, no delivery guarantees. You can fire a request and just hope that the request will reach the destination and you'll receive something back. Location transparency. In our microservices, you have dependencies of other microservices. How do you manage to handle the dependencies? Well, the go-to way is to have, I don't know, an app setting JSON for each service that will tell the service what other API are needed for it, right? It's a way to do if you do not have gateway management or API management like in cloud. If you're on-premise, pretty much is the only option you can do. So you need to implement a service discovery of some kind. So HTTP is just good for public-facing APIs, exposed to a certain client, and that's it. It's familiar, and it's very easy for us to do as the first step when we start working with microservices, and also easy to debug, right? It's common. It's so common that we do not think about them. HTTP, it's easy, the go-to option. So service discovery is an issue. We already talked about it. How about timeouts? How do you decide the time span after you will retry? I mean, is given by what? Okay, you get a timeout. Do you retry? After how long and how many times? So then you need to think about these issues, like retry policies. Thanks God Poly is around. It was actually a talk today. Circuit breaker, bulkhead, fallback, terms, patterns that help with reliability. But they're not so easy to understand and not so easy to implement, right? Just because we don't have it out of the box. How about tracing? So if you have like a pipeline of microservices that depend on each other, how do you trace the request from the first microservice to the last one? Correlation IDs that you also need to add them by yourself to implement a mechanism to be able to trace the request from the beginning to the end. Okay, so this is about HTTP, all the cool stuff that we need to implement. Okay, and after this, you say, okay, HTTP, enough is enough. Moving to gRPC. Have you ever heard of gRPC? There is also a colleague today that does a talk only on this. I advise you to go. So gRPC is contract-based. You have basically no code references. You won't have nugget packages that will reference whatever dependency you have in your code. It uses behind the scene HTTP2, which makes it inherently faster. And it also has a protobuf serialization that beats the hell out of JSON. So you'll get a smaller payload, hence a faster transport over the network. And it's available in many languages. And first-class citizen in .NET. Basically, how it looks, you will have a proto file, and then you kind of stick two APIs together using that proto file. It's very simple. For example, we have a syntax to specify, okay, this is the syntax of Proto version 3, the package name, and then you just specify what is the service. So basically, it's an interface description language, IDL, that says, okay, I have a compute Fibonacci method that gets a requested number type and return a Fibonacci result. And the requested number and the result pretty much look like this. So what happens in there, equals 1 doesn't mean that it's actually an assignment. It's the order for serialization. Okay, so next option, GRPC. As developers, we more often than not, we do not think about what it means at functional requirements, non-functional requirements. So we just do our job, we code, right? And we do not care about retries, availability of the service, the throughput that we obtain, the reliability of our systems, the latency of the network, the timeouts, and the resilience. Pretty much we kind of ignore everything. We do our tasks, and pretty much that's it. We think that this is the architect's job, right? To solve everything and to have a perfect developed system. But I think it should be in our, let's say, code of honor to think about this, because it will only make us a better developer. Okay, so thinking about non-functional requirements, we say, GRPC, how about RPC, remote procedure calls, but through a message broker, which is basically a kind of API call that looks local, but is done through whatever message broker you choose. What it does is to tie system together without code references, and helps you with the integration point and solves a few non-functional requirements. For example, if you have a request, you issue that request through a queue, and from that queue will be picked up by a handler. And the handler will just answer back through the same queue. So right now in the messaging world, our request that was standard in HTTP and everybody knows about it becomes a message. A message that can have a body that we decide to have and also has a header, exactly like HTTP requests, with a few standard properties. So if this works, what we're seeing here, it's a server and a client. And it's computing something. So we're sending the same I in a 20 seconds time span. And we're going to see how much or how big is the throughput right now compared with HTTP. Okay, so right now we processed 5,500 and something messages or requests. And actually, we kind of know that the other side got the messages, right? For example, let me show you something. I have a client that I will gonna okay, we're gonna open up, and it's sending an I as a parameter somewhere to be computed. Then I'm gonna stop this, and then I'm gonna start a new instance, and I'm gonna issue another request. What happened with my requests? Got lost, right? Nope. They didn't got lost. Just because behind the scene, I'm not using HTTP. See, the two requests that I was issuing. So this happens if you use a message broker to help you with the reliability of your system. So basically, come on. You will not lose requests as in HTTP. If you want to process faster, whatever throughput you have, you can add more handler instances. And then you can apparently spread the load. And also, for sure, you can process more requests than in HTTP. But the deal is, sometimes you need to match the request with the response, and it's still synchronous. I mean, it appears that it's way faster, you do not lose the requests, and it's a gain. But it's still synchronous, because you're issuing something through a queue, from there it's picked up, and then you get the response back. Okay, next, another step in your perfect architecture in microservices. How about messaging? So a message is basically an envelope that has a body and a header that gives you loosely coupled integration with other systems. One of the biggest and coolest things about it is that it doesn't require both systems to be up. So you can have, I don't know, half of your system down and half up. What will happen with these messages will be picked up whenever the other half wakes up or recovers. What other things can you do with messaging? Well, you can transform and transit. And terminology is called enriching a message. So you can create a pipeline of requests, and then you can extract or add more property in transit. Messaging system trades consistency for availability. You do not lose them. And common terminology, you'll find producer and consumer. Like the one side that issues the request or the message, and the one that consumes the request. Okay. So the same 20 milliseconds time span, I'm sending something to a queue. And you see that it's way, way past our numbers before. And then 20 milliseconds time span. Wait. That's the number that I've got on the same machine, on the same, pretty much the same conditions. So let me show you a bit of RabbitMQ. So RabbitMQ, it's basically a system that you install and you need to manage, that also supports masters and slaves, that you use as a messaging broker, and we're going to talk about that later. Okay, so it has an overview, and you have all the queues that are ever done through this application. You can inspect each and every queue. You can move messages, you can inspect messages, and also publish them. And the cool thing is that the messages you will have in there, we're going to stay there. So I'm going to start a new project that will just send eyes to a queue. And you'll, in here, you're going to see the messages queuing up. So no system are going to consume these right now, because I'm only pushing to that queue, but they're there. So what happens with this RabbitMQ and why I chose this system is because it was basically the first messaging system that I worked with. And once you get to know one, you pretty much can apply the concepts to each and every one, Azure and AWS and so on. Okay, so different computer than in the video. So in here we pushed a lot of messages. So those messages are in the queue. And I can see the payload and the route. And if I want to see the 3 messages, I'm just clicking here and see the eyes that are staying in there. So with async processing, basically you issue a request in a queue. or several requests, and from there, the requests are picked up by a handler. And then the handler responds to another keyword that are picked up from the other side. So basically, you need to think in terms of like pipelines when processing the requests. The deal is that whenever you want to increase the throughput, so process as much as you can, and you have a database involved, what do you think it will happen? I mean, throughput to the max, okay? But you need to process those messages and save them in database. What will it happen? You'll have a big issue because databases, okay, process more requests faster. You don't lose them. Reliability is there. Availability is there. But you move your problem to a different system, hence the database. Why it happens? Because the connection pool is scarce. So in different databases, you have, I don't know, like 100 connection pools at one time. So how can you solve that? You need to batch process the messages. Like take like 100, save them. Take another batch and save them, and so on. Or I don't know, maybe use a semaphore. So as you see, you solve some things, but then encounter different things. So still, why use a messaging system with microservice architecture? There are a few illities that I'm mentioning here. Agility, faster development. You have no integration process. For example, you do not need to publish or republish NuGet packages just because something changed in your HTTP client and you need to push them in every system that you have. You depend only on that message in itself. And the teams have full ownership in their code base. So basically, the team just know only their vertical sliced architecture. And another big thing is that you can switch technologies if you want. I mean, having an agnostic integration point like a messaging system will allow you to have maybe a microservice in Go, and one in Java, one in Python, and so on. As long as they know how to deserialize the messages, you'll be okay. Okay, in terms of scalability, right now you can scale out without too much costs. You can add more instances of the same application, or even so, in some parts of your system might add some CPU, and in other parts of your application might add some RAM. If you remember on the monolith, we could only scale up. I mean, I'm not saying that you can't, you can, but only with more money. So right now, having these isolated and independent units, you can scale only the parts that you need. You have something that is very intensively processing, okay, you can scale that on 2 dimensions. For example, if you have the login in your application, and you know that is used, I don't know, 10 times a day, why scale that? In the monolith, you had no option then to scale everything. Increased throughput. It's another dimension that it's really worth mentioning because compared to HTTP, we kind of got these numbers. We also, if you run a similar scenario, could get some other numbers, but the difference is significant. I mean, pretty much 10 times faster. 10? Only 10. Then you have elasticity for your system. You can scale up and down depending on the load of your system without using a load balancer, as we're knowing in cloud. And also, you have a lot of illities. Reliability, right? You do not lose requests right now, means that your system is reliable. It's flexible. You can distribute the load. You can increase the throughput and everything. And if we stay and discuss, I think we can find other illities also that helps with building a nice system. Okay. What are the tools and frameworks that are available for this? I'm going to mention a few. There are plenty of them. pretty much they rely on the same principles. But also, these tools and frameworks, they're split into three categories, more or less: queues, actor models, and message brokers. The queues, we know them from high school. It's useful. They are useful for point-to-point communication, service to service, and that's it. Messages in here are timestamped and ordered, and the receivers are pulling the messagings from the queue are not notified that, you know what, a message it's in the queue and you need to process that. An example would be Amazon SQS. Actor model. Have you ever worked with aka.net? Cool thing. We need to talk about that. I didn't got the chance to work. I always wanted to try. The actor model is born from the reactive programming, where actors are processes that encapsulate behavior and handle concurrency very well. So two examples of these are aka.net and Orleans from .NET, and are born from reactive manifesto, at first mentioned in '73, so it's an old concept that surfaced very recent in time. The reactive manifesto basically said that the modern web needs to be very fast to respond to the data load, and to be message-driven, and to be resilient. I mean, self-healing systems. Now it's a concept that it's getting it more and more traction. So we should build systems that are able to recover from failures by themselves. So, for example, 3 seconds page load on the web is not acceptable. I mean, if you wait as a user 3 seconds to see a page, you're pretty much gone off the page. Message brokers. So what happens in message brokers is that one process sends message to a name, queue, or topic, as you will hear in Azure. You can have one or many handlers or consumers, and handles connections and disconnections very well. And also, if a message cannot be processed, it will go to a dead letter queue. So either way, you're not gonna lose that request. And also, it has pretty much 3 types of message guarantees, and we're gonna see how what are those, and different protocols: RabbitMQ, ActiveMQ, ZeroMQ, Kafka, NATS, and so on. For example, NATS is used by HTC, Siemens, and VMware. So major players in the industry are using that. Guarantees exactly once, so each message will be processed exactly once, at least once, or at most once. And depending on the guarantee type, you'll have more or less issues with the systems, or you need to reorder the messages and so on. So this could have a workshop day just to understand all this, but it's worth mentioning. So RabbitMQ, you already seen that. It's lightweight, it's first in, first out as a process, and also supports AMQP protocol. Have you heard of that protocol? Yeah, very nice. It's easy to use, it's fast, and by default it works with at least once delivery. And AMQP as a protocol, Advanced Messaging Queuing Protocol, it was born from the telecom world long time ago. It's async by nature, unlike HTTP, and it has guaranteed message delivery, and also it has absolutely no DNS resolve for each connection. So in HTTP, if you created a new connection and you wanted to make a call to another API, the API had a DNS. If it was in production, more or less had a DNS, right? So that DNS needed to be resolved, which means that it took more time to resolve that and then process the request. Also, AMQP has the programmatic routing. So you decide where your message will go. It has retries out of the box. And also, out of the box, you can acknowledge or not acknowledge a message. So for example, if you decide that a message was processed or incorrectly, you want to discard that, you can not acknowledge that, and it will go back to the queue. Another thing that is very cool about AMQP is that it has the channel concept. A channel is basically very similar to these wires in here. So the connection is the outside, and inside you can communicate back and forth through channels. So from the inside wires. So this channel has help you just because, well, you do not need to open a new connection. You have one, and then you send messages in that connection. So also it handles connection and disconnection very well. How do you direct exchange stuff? So also having a message, an image, for example, you can decide to send that image to different queues, depending on what you add there as a key, a routing key. For example, if you decide you can go to something that will be processed and cropped the message, and then maybe using a different routing key, you can send it to another queue to be resized. So you decide where to send the message. And then maybe you have a scenario where you can fan out the message. You need to let handlers to be notified that something happened. And also, another thing that is possible in RabbitMQ is that you can add patterns to the queues. And depending on that pattern, it will go to a different handler. For example, maybe you have a log, and you add the severity log in there. I don't know, warnings, maybe you can send them to a different queue. High alerts or, I don't know, informational stuff, you can send them to the dev team to be notified that they need to wake up and fix the issue in production. So you can handle things very nicely with topic exchange. Also, this word topic, you'll also find it in Azure as Azure topics. The concept is pretty much the same. I added in here a few references. There are these two books that really contains stuff about integration patterns. They're heavy, but very nicely written. Designing data-intensive applications and enterprise integration patterns. Pretty much you'll find everything you need in here. For example, knowing about AMQP as a protocol helped us to double the throughput and the processing of the messages in a specific system that I worked. For example, Azure comes with its own protocol, and switching that to AMQP basically doubled our throughput. And it's nice to play around with this because knowing the protocols will just only make your systems better, and you'll get just more throughput, more availability, more scalability out of the box. Without changing, for example, in Azure, it was just to change from their default protocol in a connection string to AMQP as a protocol. So not hard to do, but you need to know what are the options for you. So bear in mind that the distributed systems, so our microservices and APIs, are all about trade-offs. So we cannot have the perfect system, but at least we can aim to have the perfect system. So I'm not saying not to use HTTP clients. You go ahead and use them, but leave your architecture able to evolve. Okay, go with HTTP. Next step, come back and switch to GRPC maybe, because it will leave your code cleaner. You won't have the coupling issues with NuGet packages scattered all over your projects. And then came back after a while and moved to messaging. either RPC through queues or fully messaging brokers, whatever it is. But just go back and evolve your architecture because the benefits are huge. The only thing is that at first, it's not hard to grasp because the concepts that you're working with in a messaging world are different that you're used to. I know that for me it was pretty much difficult at first to switch. Okay, this is basically a request that I know from HTTP. Now it's called a message. Now I have some handlers that are processing those. I'm processing those, but what happens if those messages aren't processed correctly? And then what happens if it goes to the dead letter queue? How do I extract those from there and retry them? Okay, what happens if my RabbitMQ dies? I mean, okay, I have everything in there. Some might say that is the single point of failure, right? I mean, you have one system that you depend upon. So how do I work everything out? Thankfully, I had a DevOps guy that took care of RabbitMQ. And hopefully, if you're lucky enough, you can be in cloud and everything pretty much will be handled for you. You won't need to be worried that, okay, cloud will be down. It shouldn't be. So you won't lose any messages that you have in there, either in that letter queue, either in your system ready to be processed. So choose wisely and think about NFRs. I know it might be a lot and yada yada from one girl that sits in front of you, but those things are important. For your clients, it might mean a lot of money, or it might mean that they can gain some extra business from that, just because the system is very fast and reliable and secure. So keep in mind that HTTP is not the only option, and always revise what are the options. Don't choose just because it's easier. I cannot, I can't understand that, but there are other options, and now there's a hype around architectures. And also, don't say that your microservices uh, are micro state of the art if they're not. Call them services. I'm not saying that you're not doing perfect systems, but as a funny story, I landed on a project, and the guys from there, 70 guys, um, they bragged about themselves that they're doing state-of-the-art microservices, REST, and so on. And they were doing HTTP calls all over the place, and their REST APIs weren't so REST. They had like /new in the URLs. So revise your architecture and try to learn from your mistakes and get back whenever a mistake or something that can be improved is found. So if you have any questions, go ahead. Thank you for being here. You can also DM me if needed. And I hope this talk was good for you. Thank you.